All right, so foundation of deep learning, me again. All right, yeah. So again, do interrupt me. It's going to be the last class we have in person. We have a very bad situation, especially in Italy. People are dying. We don't have any more beds in the hospitals. We don't have doctors. Doctors are working like 24/7, and they are going home and they are affecting their own families. So it's like a really bad situation right now back home. And it looks like we are 2 weeks away from that situation over here. So just wash your hands. Try not to go in very crowded places. Stay healthy, okay? Please. All right. Let's start class. All right, self or unsupervised learning. Generative models, capabilities. So here I'm going to be giving you some eye candies such that you can get hungry. And then I can feed you with the first part of this lesson. This lesson is going to be split in 2 parts. Half is going to be today, half is going to be online through the Zoom, I think, system. So, hands up, who thinks the picture on the left is real? Okay, now hands up, who thinks that the picture on the right is real? Okay, who thinks that both of them are real? Who thinks that this one is fake? Who thinks that this one is fake? Who thinks that both are fake? Okay, you are right. So these 2 images have been generated by a model that we trained. Actually, this guy, Kara's trained. So if you go on the website, this person does not exist, you can find several examples of very good-looking, non-existent people. If you keep clicking, sometimes you're going to find some person with a hole in their faces. That's kind of very easy to recognize that is not quite likely a real person, but otherwise, all of them look pretty legit. You can notice that they have very nice teeth, very nice, chicken feet, like things. What do you call them? You can clearly tell here, though, that if you check on the background behind, the network is not producing a very accurate background, although the faces looks very good. Why is that? Because the network has been provided many samples, and those samples are refiguring faces. The thing that is not constant is the background, right? So the background is the variable here. And therefore, you can't learn any possible background. So the background will look like some weird stuff because there is much more variability than what are the possible appearances of a face. Given a face, in how many ways can you distort a face, a human face? Like, if your face, how many degrees of freedom does it have? Huh? You know this answer, right? We already covered this in class. 8. He said 8. How much? 1,050. No, just 50. 50, yeah, that's 50, correct. So you have roughly 50 muscles, something less, plus, rotation, tilting, and what's not. So, all possible, it's just a manifold in 50 dimensions. So everything else doesn't quite, is outside that manifold. Although this picture, are several megapixel pictures, so each point here is living in this huge dimensional space, although all the possible variations are restrained to a subspace, okay? So that's the training manifold, the data manifold. Okay, check out the website. Okay, so we have here a very cute doggo, and on the other side, a less cute bird. Sorry, yeah. If you do a linear interpolation between the doggo and the bird, what are you expecting to see in the middle? And for this one, I'm going to be actually turning off the light. Turning it back on next soon, after.
Blurry?
Again?
A blurry image?
So, a blurry image, what do you mean? So, what do you expect to get over here? Roughly. Yeah, you can talk back. So I'm gonna be doing 100% this one plus 0, 90% this one plus 10%, 80% this one plus 20% this one. So what are you gonna be seeing here? You should guess you're less than usual, so you actually had to talk back more than usual.
Flying
squirrel or something.
Flying squirrel, no, okay. So you have a dog, you have a bird. If I do like a linear interpolation of these two images in pixel space, what do you get?
One imposed on the other.
Say again, sorry?
Like one image imposed on the other.
Yeah, superposition, right? So you're gonna get something that looks like this. You get basically overlay of the first image with the second image. All right, so let's get back here. And instead, let's do an interpolation in the latent space of the network. So I input both those two guys. I get the two representation, those hidden layers. Then I do a linear interpolation between the hidden layers. And then I do the decoding part. What do you expect to see here? And you still have to talk back to me. You have to shout.
The background will probably still be a mess.
The background is still a mess, but then what's going to be the subject?
It'll sort of be like halfway between.
Right. So you're going to be starting seeing a birdie dog and then a doggy bird, okay? And that's how it looks. Birdie dog and a birdie dog and a doggy bird, okay? All right. This is a network that did this. Atrocious, right? It's blasphemy. You should watch Full Metal Alchemist episode where the father takes the daughter and the dog and makes something similar. It was so interesting. Okay, if you watch cartoons. Brotherhood, right? The second season. Okay.
Why does the sky disappear so fast?
Aha. I don't know. Because it's a lot of green, so I guess it got rid of it. I don't know. I guess I don't know. Good question, though. Good eye. So let me show you a few more. So this stuff comes from Brock's article. And that, okay, you have a smaller, so the first one, you have a small version of those images. We start from something like looks like a shark or a manta, I think is the name. Then that stuff looks like a polypus, or how do you call them? Say again? Octopus, right? No.
Oh, octopus.
Yeah, something like octopus. And then the octopus becomes like a monkey, and then it looks like a dog, right? So you can see the shark becomes an octopus, that becomes a monkey, that becomes a dog. So interesting, like how you can change breeds by just having the final 2 points fixed, and then you walk through the latent space. So you have another one here. You go from this puppy here to a bird. So again, you have a birdie, a squirrel, whatever. And then you have a bird, and then the other side you have a doggy. Or this one, you have like the smelly guy, what's called? Skunk. Skunk, thank you. Oh, that's why you smell like a skunk. It's the same, right?
Yes.
Huh, okay. I see. So you have a skunk here, and then you get to a dog, right? But it actually looks a lot of a dog after this thing here. And finally, you get a bird turned into a fly. I think these are pretty awesome examples. So this should make you hungry, such that I can feed you with the second part of the class.
All of these images come from the same.
Right, so you have this image on one side, you have this image on the other side, you get the embeddings, and then you do some basically interpolation of the embedding. You can check out the paper for more details. The point here is just to show you that the difference between interpolation in pixel space, what is the difference between interpolation in pixel space and in the latent space? So the latent space capture what is the basic semantic of an image, and therefore you go from the pixel space, which kind of doesn't really play well with our tools, to kind of more well-behaved space, which is our internal hidden representation of the data, of the network. Again, this is just to give you some appetite, right? I'm not formal at all. What next? Okay, you can zoom on dogs, you can shift on the X, on the Y, you can change the brightness. The interesting part here is that when you change the brightness, actually you change day to night or night to day, because that's what the most normal brightness change in pictures looks like, okay? So whenever you change brightness, you actually change the time of the day. Or you have a 2D rotation or even a 3D rotation. This is so interesting. Means that a network can somehow have an internal representation of the 3D world. That's something Jan was mentioning yesterday. If you shift, a little bit and you see this kind of parallax, then the easiest way to express, to basically address this phenomenon is actually to imply that there is a 3D world, okay?
So the idea is that there's one parameter per per one of these things in latent space?
So in this case, they train the network in order to actually be able to handle specific transformation. Actually, I had to put the reference on this paper. Again, I'm just giving you some, how to say, eye candies, okay? I'm not giving you any formal thing right now. In this case, actually, I like this one so much. You can get the anime version of your picture, right? So you could try this out, but don't try with hentai, right? We don't want to do those things. Okay. All right. So some of you actually know this stuff. Interesting. Okay. Right. The one that don't, it's okay. Just forget. All right. Okay, this is other stuff, which is pretty cool. Like you can go from low resolution to high resolution. From the left-hand side to right-hand side. And here you have a few examples, but this is, of course, is black on white. It's much easier to do this stuff, and the same for the zebra. And this is a pre-deep learning technique, so they were just using some hierarchical model. Nevertheless, it works pretty well. And then a few years later, you actually get Garcia getting you, really high. This is like the upsampling by doing like linear interpolation. And instead, this one is going to be the upsampling done with the neural net. And the final one is actually the real image. You can see clearly on the third row how this Asian dude became European. Why is that?
Training set?
Bias, right? Correct. So the network has seen a lot of white dudes, and therefore the easiest way to reconstruct a kind of unknown face features is going to be to plug their white dude face. Or this lady looks like she's having a stroke because we don't have many side views of these images, right? This lady changed sex on the bottom side, and then this guy looks like he had an accident. Because again, we didn't have many glasses on the dataset, therefore the network, saw some very dark thing and then, implied someone just punched him very hardly. Okay, but again, this is very old stuff. I mean, we are 4 years in the future now. Again, these are the first results, and this allows you to leverage, actual data in order to fill in the gaps. And the gaps are what are the actual detail. We have very, very many new results recently, but these are the kind of pioneering examples. One more. Here you basically block the face with a gray square, and then you ask the network to reconstruct the face such that it gives you the best looking closing point, right? So you take an image, which is staying on the training manifold. You put a patch on the face. This patch will make the image go away from the training manifold. And then you can do, for example, gradient descent in this energy space such that you can find what is the closest point, like the point with the lowest energy, that is associated to that specific initial image, okay? So you get an image, you perturb the image, that makes it go away from the training manifold, and then you can do gradient descent in the energy landscape such that you can pick whatever sample looks like the most, it's on the closest sample on the training manifold. And this is some stuff Jan was covering yesterday about energy-based model. Whenever you learn an energy, then you can actually use the energy to do inference. To do inference, you actually have to minimize the energy, right? So energy minimization means inference, not training. Training is something else. Again, we are going to be covering more detailed energy-based models in the following classes. Here you have another few examples, one using a variational autoencoder and another using generative adversarial net. This is also another example from Reed. This is crazy. You can go from English description to actual drawing of what the English description mean, right? So you go from a sequence, I guess, to a vector, which is like the concept, and then from the concept, you use a decoder, so it's a generative net, which is going to be decoding your specific output. And that was pretty much it for the eye candy. So this should make you very hungry for the second part of the class. Are you hungry? Yeah, I didn't have dinner either, but okay. All right, so autoencoders. What are this stuff? Unsupervised learning. So this is our first model we're going to be diving into in order to see how we can train a network without targets or labels. What are targets? What's the difference between target and label? You already know everything. Someone else. Prediction means both of them are actually given, both of them are annotations.
Label's categorical and the other is a real number.
Thank you. So labels are going to be categorical. You can label things. This is a chair, that's a table, that's a door. Targets are going to be, you know, in the target, right? Okay. All right, so we're going to be observing how we can train this model without actually having targets or labels. So this is the first network, which is the architecture we are going to be playing with. It's very similar to what we observed so far, but the big difference is that we start from the bottom. We know already why. It's pink. You go to an intermediate hidden layer in green, and then you get top to the input. So the output of the network is going to be the prediction of the input. Okay. So you have also a different kind of representation. You may have, so those are the equations. The hidden layer is going to be the rotation, squash rotation of my input, and then the final output is going to be the, I guess, squash version of the rotation of the hidden, okay? Where rotation means affine transformation. We have some dimensionality, so we shoot towards D, but then both x and x hat live in the Rn. Therefore, the second part is going to be our generative network. This one that goes from H to X hat is going to be my generative net. And here you have a different diagram, which is basically doing the same thing, but this one is, you know, some people prefer these diagrams where the actual transformations are made in boxes. Okay, so you have people saying this is a 2-layer neural net, although we know that is a, how many layer neural net? How many balls you see? 3 layers neural network, fantastic. That's my convention, okay? If we use Jan's notation, then we also have, okay, hold on. So you actually can have some tight weights in order to be trying to reproduce somehow PCA, although you don't have guarantees over the order of the different weights of the different bases. But if we use Jan notation, we are going to be also adding those kind of little projectiles there, which are representing the transformations, okay? So why are we using autoencoders? What's the point of predicting my input? Let's say I use an identity matrix, okay? I provide input, which is a vector. I multiply this vector. I do an identity matrix times my vector. I get the same vector. That's an autoencoder. So you get the same thing as you put in. Why the hell are we doing this?
Because when you're predicting, you're not going to have the input.
So you don't have the input when you predict, but then I can just learn the identity matrix, right? I have identity matrix, I put something in, I get something out. I put something in, I put something out. I put same thing in, I get the same thing out. So the most trivial thing to learn for a network would be the identity matrix, right? The thing I put inside comes out. And that's how we train this stuff.
If D is less than N, then you cannot have identity matrix.
Say again, sorry?
If D is less than N, then you cannot have identity matrix.
If D is
less than N.
less, right? Okay, there is a first point. So if we have a, what's happened? If we have an intermediate dimensionality D lower than N, therefore we can start seeing what this stuff can be used for. For example, it could be used for compression. So if I have an intermediate representation which takes less space than my input representation, I can use this encoder as a compressor. And then I have my hidden representation, my code, which is, you know, addressing what the specific input is. And it takes less space. So I can use a, you know, image compressor, for example here. So that was my initial idea for autoencoders. But that's just one type of application, and it's kind of, you know, not the proper way of thinking about these guys. So an autoencoder task is to be able to reconstruct data that lives on the manifold, okay? So we have a data manifold. We get some points. We have data points. I use these points for training my system, and I'd like my autoencoder to be able to reconstruct only things that live on the training manifold, on the data manifold, okay? So that's actually what what is the task of these autoencoders. Only to reconstruct a small subset, and I'm getting tripped off by my microphone, one sec. Okay, this is too short. Okay. We should be only able to reconstruct, we had to enforce only to be able to reconstruct a small set of possible inputs, okay? Now it becomes interesting, because if you can only reconstruct a small set of inputs, then you cannot reconstruct things that are away, right? And so, for example, like before I show you, I put a picture, I have a picture and I have a gray box in front of my face. So I take my point and I take it away from my training manifold. If I try to reconstruct it, and my network can only reconstruct things that are on the manifold, it will reconstruct something that is here, which doesn't have that patch on the face, okay? Do you see this or no? So if you're only constrained to reconstruct things that have been observed during training, any variation that you apply to the new inputs later on when you're going to be using this network is going to be removed, because the network will be insensitive to that kind of perturbations. So let's see a bit of more details about this stuff. Is it clear so far? Yes, no. Okay. All right, so let's figure out what are the reconstruction losses we can use. So the first one, we have the classical loss for the overall data set. Is going to be the average between my per sample losses, okay? And so there are two per sample losses. The first per sample loss is going to be the binary cross entropy, which is going to be penalizing a lot if you make a mistake. So the output, the targets are going to be 0 or 1, so you have a categorical distribution. And then your input is going to be, your output is going to be something that also lives between 0 and 1. So you have a sigmoid network, a sigmoid nonlinear function at the end, and then you try to minimize this guy here. Otherwise, if you have real value inputs and outputs, which are, for example, images, color images, you may want to use the MSC, okay? All right, so as your friend there mentioned before, we have, it's pretty obvious to think about like a under complete hidden layer. A under complete hidden layer has a dimensionality which is smaller than the size of the input. So in this case, the network cannot perhaps copy or use the identity matrix, because you have an intermediate representation which is smaller, and then you have to expand this one back to the original dimensionality. Again, you can use a under complete hidden layer autoencoder for doing compression, for example. Okay, so this is pretty standard, I would say. Does it make sense so far? Okay, so we're going to play with this in a second on the notebook. Nevertheless, I will say I actually like this one more. And you are going to be telling me why. You should be able to, you should have all the ingredients. It's going to be, this is the 6th week, I think, 7th week, right, I think. I'm not sure. Why do I want a larger intermediate representation?
Expanding it into a space where you want the network, you want the encoded version of the input ideally to contain as much information about the input as possible. So if you're expanding it into a space that's larger than the actual input space, it might be easier for the network to learn over that space.
Okay, did everyone hear him? No, try again. That was correct intuition. Just shout a little bit louder.
You want the network or the encoder encoding to extract as much information as possible from the input. So if you expand it into a space that is larger than its original, the original space it belongs to, then the features, it's easier for the network to extract more features out of that because it's more sparser and it's more spread out.
Right, so we always said that the larger we go in the intermediate representation, the easiest is going to be the optimization, right? And so, although the information that is contained in the first layer and in the hidden layer is going to be the same, I can't add information. But it's much easier now for the network to play with a representation that has many more dimensions. The point is that we can simply learn now the identity matrix, and we are going to be just copying everything. You copy the first guy in the first spot, second guy you copy here, the third one you copy here, then you copy everything through, and you haven't learned nothing. You haven't learned the identity. Therefore, we have to apply some other types of constraint for the information. And so we have to learn how to introduce now a information bottleneck, okay? Although we enlarge the intermediate representation, we have to constrain the representation. We have to constrain the possible configurations that the hidden layer can take, okay? The input layer can take as many configurations as you want. The hidden layer should be only containing the possible configuration that the training data, the data on the manifold can have, okay? So the input can be everything you want, but you're going to be training only with data that is on the manifold. Therefore, the hidden layer has only to be able to model, to capture what is the variability within the training data and be insensitive to anything that is outside, okay? Such that we can have a selective reconstruction of a subset of this very large input space. Are you with me? Yes, no.
Overfit the training data?
Unless, we are going to see now how we avoid overfitting on the training data. So there are a few ways to do this, make this stuff on the right-hand side work. And moreover, you may want to you can have the same rationale also for this left-hand side guy here. So let's say I have a super awesome decoder. Then my encoder could simply put all my training data as, first training data is first point. Second training data is going to be number 2. Third training data sample is going to be number 3. So I can associate each of my training data as one number, 1, 2, 3, 4, 5, 6, 7, whatever. And then you have the decoder has memorized all the training data points. And then you just output the training point that you want from this kind of selector. Right? So you potentially may only need one ball here, only one neuron in the hidden layer, in order to have a network that does overfit, as long as the decoder and the encoder are very powerful. Okay? So the point is, your colleague mentioned, how do we avoid overfitting? This stuff can overfit too. This stuff will overfit unless we are, careful about how we design these things. And so there are a few different methods. There are contrastive methods. And there are regularized methods, and there are architectural methods. We have seen yesterday as well something. We're going to be covering now a few of these. And we have 20 minutes left. Okay. Yeah?
Sorry, so in the example with the gray box, would the image of the gray box be X, and then what it should be the X hat? Or?
Next slide, yeah. So denoising autoencoder, how does it work? I take my input, the pink one, I put it away from my original point. So these are my this is my data manifold. Each of these points are going to be, samples I'm going to be providing for the training. I take my point and I displace it, okay? How? I just add random crap, okay? Cool. Now I enforce the network to be reconstructing that initial point. Right? So this is a denoising autoencoder. You take a point from your training manifold, you take it, you move it away, and then you enforce the network to take it back here. I take the same point, I take it away on the other direction, and then I put it back here. I take the same point, I put it in another direction, and I put it down here. Okay? So what are we learning right now? We're going to be learning a vector field, which has everything coming back to this point. Then I start moving around my training manifold, and I have all this kind of vector field, like the vector field is going to be all pointing towards the training sample, right? But if you have a training sample here and a training sample here, this guy will try to attract here. This one try to attract there. So things that are on the manifold stay there. Things that are outside the manifold will be, collapsing towards the manifold, okay? Questions? Okay. All right. So actually, there is a caveat. Caveat, right? Caveat. How do you say? Caveat. Thank you. All right. We assume that we are injecting the same noise distribution we are going to observe in reality. In this way, we can learn how robustly recover from it, right? So if we assume that we have access to the type of perturbation we are going to be observing later on at inference, then we can train the model to be insensitive to those kind of perturbations. And this is a very big if, okay? Therefore, nice pictures, okay. All right, so this is my training data. This is the pink points. And I'm going to be turning off the lights. So I have here my pink points, which look white to you. Then I have the orange points, which are the displaced points, okay? So they are originated from these points here, and then I displace them in many directions. Then I train my network to get all these orange points back to original starting point, right? And so this is the output of the network. I input this cloud of orange points in the network. I train my network to output the points on the actual spiral, and therefore these are the blue points, are going to be my reconstructions of the network, okay? So if points were already on the manifold, they didn't move. If points are far away from the manifold, they moved a lot. Guess what? I can measure how much they moved, and that's going to be your energy. How cool is this? Huh? Okay, maybe you haven't understood yet. So in this case, in order to be a bit more thorough, I just send every possible x-y combination on this plane inside my network, right? So here you have this line because all these bottom left corner got squashed down here. And then you can see here points are quite sparse, and then there are very, very many of them densely occupying the manifold. Nevertheless, there are a few points here, right? And so this is showing you with colors what is the distance those points have traveled. So points over here in the bottom left corner have traveled 1 unit, and they got down here, I think. Points over here travel also like 0.9 something, and they went down here. As you can tell, points within these two branches didn't go anywhere. Okay? Why is that? They are attracted by both points on this side and both on this side, on average during training. Nevertheless, if you forget about, having stuff that is curling on its own, you have everything just drops down to here. Guess what? I can put the points that have just moved a little bit again inside the autoencoder, and I can keep doing this a few times until these points collapse down to the manifold, okay? All right, or I can do something cool. Cool, but it's a trick, right? So what did I do here? This is my denoising autoencoder, where I get to the initial point, where I start from, my displacement from, right? So I got my initial point I displaced, and then I forced the network to go back to the initial point. What happened here? How did I fix this? How can you fix this ridge here, this dark region? Any guess?
Make it move randomly in one of the directions?
You can send them randomly, or
The direction.
hold on, someone there, top right. Push it up. How do I push that up? Oh, okay. Pushing up would be also very good. So I also tried to push up everything that is not on the manifold. Didn't quite work. What did I do here? It's a hack, okay? It's not elegant. It cannot be done in a high-dimensional space. So what I've done here is going to be make your point fall on the closest point on the manifold. And so I did an exhaustive search of the closest point on the manifold, and then I enforced my network to always make my points fall on the closest point, although they were maybe generated from another initial point, right? So if this point over here initially originated from here, but it's going to be always falling down on this direction. Just a few points will not be, they are just in the middle way, and they don't fall anywhere. All right, so...
Is the problem that that's computationally impossible when you go to more points in more dimensions?
No, in the more dimensions, everything is far, right? So it doesn't quite work. Oh, we haven't covered that notebook yet. Okay, I'll show you next time, I guess. Well, next time.
Can you explain what you did again?
Yeah, so in this case, I've done the denoising autoencoder. In this case, I got the displaced point to fall onto the closest point on the manifold. So I did an exhaustive search. It's simple because I have 150 points here. But it's a hack. You cannot do that in reality. Anyhow, the point is that we kind of have developed some kind of understanding. And this one instead that Jan really likes, but I am not yet able to make it work, so I guess I'm not that smart yet. It's regularized autoencoder. In this case, I have a L1 regularization term, cost, on my hidden representation. So I force my network to come up with hidden representations which are short, and they are like short of a few dimensions, right? So if I have a L1 regularization of my hidden representation, I will only have a few items active at a given time. The problem is that if you set all those other elements to 0, then you have 0 gradients to send back, okay? And so then you may want to use target prop and other cute, fancy things, and I still am working on this, so I have no idea how to make it work. The point is that this is the regularization term, so this is the L1 penalty on the hidden representation, and this black dark here region should be actually extending all around. Again, it's very hard for the moment for me to get this to work. Not saying that it's impossible, I'm just saying that I'm not smart enough. All right, contract the autoencoder, and then we're going to be seeing the notebooks. Let me turn on the light such that, or maybe not, I don't know. Shall I? I like it so much dark. Okay, whatever. Okay, back on the camera. All right. Again, data manifold, points, training points. What is the contracted autoencoder doing? So this guy here, it simply have the reconstruction term plus that thing here. What is it? Gradient of my hidden representation with respect to the input, norm, square, in the overall loss, right? So my overall loss will try to minimize the variation of my hidden layer given variations on the input, okay? So here you want to have a representation for the input which is not changing that much as I wiggle my input, okay? And so this one basically makes you insensitive to, insensitive to reconstruction, penalizing insensitivity to the reconstruction directions. So you actually will be able to reconstruct things over the manifold, but it will make you otherwise insensitive to any other possible direction. And so this one, we don't have an assumption over the perturbation I'm applying. I'm just insensitive to everything, but then I still have many points here, so you will have to minimize the reconstruction as I provide different samples. Okay? And yeah, penalize and incentivize as well. And that's just penalized. Finally, okay, 10 minutes left. Finally, what does this autoencoder do? As you can see, I can use matplotlib very well. Here we have this training manifold, which is my single dimensional, thing going in 3 dimensions. And here I have all those data points, okay? Cool. So the X lives on this set of data, and it lives in Rn. What an autoencoder has to do is going to be basically getting that curly line stretched down in one direction, right? And therefore, you have there your Z. In this case, it's called latent space. And so you get the first one there, and then the second one over there. The point is that how do I know, how can I go from this back to here? I know if I'm in this first location, I can go back to this location. I know if I'm in this location, I can go back there. I'm not entirely sure what's happening here. I only have training samples, right? So I only have the correspondence between points in the input space and points on the latent space. I don't have any correspondence between regions of the input space and regions of the latent space, okay? So as of right now, you only know how to connect inputs to regions here in the latent space and how to get back. Then we have learned that the denoising autoencoder takes the input, shakes it, but you enforce to go back here. same point, and then you go back to the other location to define a location, right? So you take this one, you shake it, it's going to be always going here, and then you get back to the correct location. Or the denoising, the contractive, you're going to be the input, and you try to penalize any possible wiggling of this one when you wiggle this, okay? This is contractive autoencoder. Nevertheless, how can I start from here, move around, and get something that actually looks like a decent output? Meaning, if I translate this one, if I have a dog here and a bird here, the embedding the latent space, if I move on this line, how can I assure that the things on this line here will actually look like meaningful transformations in here? We don't know that. Right now, we only know that this image is connected to this point. This image is connected to this point. We don't have any knowledge about what kind of behavior or how well behaved this space is whenever I move in this space converted down here, right? So we don't know how this decoder that goes from the latent space to the input space is behaving when we are not exactly in the points, right? So right now we have points mapping only. Next time we're going to be learning how to map regions of the input space with regions of the hidden space, okay? Right now we have point. All right? So notebooks in the last 7 minutes. Thank you for sticking with me. Yeah. I'm moving too much. I'm panting. CD, work, GitHub, PDL, Jupyter, Conda, activate, PDL, Jupyter Notebook. Okay, so I'm going to be using this autoencoder, just the number 10, okay, over there. It's invisible, I know, but it's going to be number 10. Okay. All right, so I'm going to be just executing stuff through. Okay. All right, so what are we doing here? Let me see. We import some random crap. Can you see, right? Yeah, you can. Complain if you don't see things, right? I can't check too many things. So we import some stuff. We have an image conversion routine, which is simply adding 1 and then multiplying by 0.5, because I have otherwise my data. When I get my data, I try to get it 0 mean, and I have also in a range that is between minus 0.5 to plus 5. So it is centered. Then here to get it back, I sum 1. So instead of being 0 mean, you go 0.5 mean, and then I actually have. Oh, sorry, it starts from minus 1 to plus 1. Then here I just sum 1, so it goes from 0 to 2, and then I get it 0 to 1. This is just some displaying routines. And here, okay, I show you that I subtract 0.5, and I divide by 0.5 my data. Those are the MNIST digits from Jan website. Here we set the device, if you want to run on CPU or GPU. And in this case, we have images that are the digits. We saw that when we were training the convolutional net, which are 28 by 28 pixels. And in this case, I'm going to be creating an autoencoder which has a 30-dimensional intermediate layer, right? Hidden layer. So we go from 784 to 30, and then back to 784. So here is going to be my autoencoder model. Just a linear layer, a fine transformation like, 28 squared to D, hyperbolic tangent, and then I have the decoder, which is my generative model, which goes from the hidden space, the latent space, which is D, to 28 squared. And then I have, again, a hyperbolic tangent, such that I limit my output range to minus 1 to plus 1. And my forward simply is going to be send things through the encoder and decoder. I create my model, and then I create my criterion, which is going to be the MSC loss, learning rate, and Adam optimizer. And so this is going to be the training part. So you're going to be having whatever, 20 epochs. The first part is going to be sending the images through the model. This is number 1, right? Number 2 is going to be computation of the loss, which is line number 15. Then third point is going to be clearing the gradients, otherwise we accumulate, so that's number 17. Then we do backpropagation, computation of the partial derivative of the final loss with respect to the weights, that is number 18. And finally, we do a step backwards in the direction of the, so you see that's the direction of the gradient, you step backwards. I'm talking a lot because the computer is just training, okay? All right, so you can see here we went through 20 epochs. And actually, let me show you how they look. So these are the reconstruction of my network, okay? These are the output of the network given that we compress them to, that's 30-dimensional intermediate representation. I'm going to show you the kernels in a sec. Let me change this one to a denoising autoencoder. So here I create a dropout module, which is randomly turning off neurons. I create my noise mask, and then I create my bad images, which are multiplying those images to this binary mask. And then I send to the network those bad images, these alterated images. And I train this stuff again. We also like to get to 500 dimensions, right? So it is overcomplete hidden layer, and then we train again. Okay, this is correct. And this is training. Okay. All right, so just recap of what's the difference between the previous training and the current training. All right, so we were saying that before we were just using a undercomplete autoencoder. So we were going from 784 dimensional as an input to a 30-dimensional hidden layer. But now we are going to be using an overcomplete. Still, I use 500 here, which is less than 784. So one proper question would be, why are 500 dimensions, why does a autoencoder with 500-dimensional hidden layer is considered or can be considered overcomplete? Think about the number of pixels that are black, for example, on average in these images. All right, so we actually already ran this part. So we were down to the training. How does the training changes? Right now, I have a dropout mask here, which is allowing me to introduce some kind of perturbation on the original images. Then I have my noise, which is simply applying a dropout mask on a vector of all ones. This is going to be useful for later visualizations. Then I create my images bed, the perturbed images, which are simply the multiplication of my image times this noise. So if we didn't have any neuron dropped, the noise would be just those ones, and then you get 1 times image, so you get the same image. Otherwise, when the neurons are dropped and set to 0, the image now is going to be multiplied by 0 for those specific values of the pixels. So these image bed are images with black dots. Then I input inside my model this image bed, okay? And then the criterion, it's between, it's the distance between the output and the original image, right? So before we were, in here, we are inputting these perturbed images inside the model. So those are points that are outside the training manifold. But then I enforce them to be the original point, right? So you get the original point, you perturb it, so you put it away, and then you enforce the network to actually output this one. So it's going to be trying to contrast any kind of perturbation that happened to this original point, okay? All right, the rest is the same, right? 0 grad, backward, and step. So this is also trained, and we can check how this reconstruction look. And if I can remember from the previous iteration, they look much more actually clean, because I guess we are using a much larger hidden layer, right? But before we couldn't use such a large hidden layer because you would have been overfitting, right? If you try to reconstruct things that are always in the same point, you just can copy them over. In this case, you can't copy, right? Because the input is not this point, but the input is actually the displaced point, right? So you learn a vector field that is bringing you back to the original position on the training manifold. Okay, so let's go down and let's visualize actually let's have a look to the previous filters I didn't show you. So these are the filters of the autoencoder with a undercomplete hidden layer, okay? And so you can see here there are some kind of patterns in this central area of these filters. So these are the filters, which are simply my rows or my W metrics that have been reshaped in a basically in an image such that I can visualize for you. So in this case, in this notebook, we are not using any convolutional network. We are just using those images that have been unrolled into vectors, and they are compared, they are multiplied like scalar product against the vectors, right, of my matrix. So these are the rows of my matrix that have been reshaped such that you can make sense of what they represent. So here, for example, it looks like there is like a upper loop detector, or not detector because they are purple, right? So these would be negative, the output. Here you have like a 0, here looks like some 8 or 3, and then you have this kind of, this kernel over here that has basically learned nothing, or, well, that's the only one that didn't learn much. Moreover, you can notice that all those points outside the region where the number happened, or where any kind of interesting thing happened, all these points are multiplied by a constant, right? Because it's outside a digit, and so things don't change there. And therefore, these noisy kernels over there, on average, they will produce a score of 0, right? And therefore, you're going to have that the network didn't care about giving any specific value to these outstanding, these outer points, outer pixels, because again, on average, they will not contribute to the final score. What happened now? When we are inputting the data which have a variable amount of like pixels set to 0, now these points will matter, right? Because it's not longer continuous, the value of the image. And so if I show you the new kernels, boom, how cool is this, right? This is completely different. Can you remember? So here you can still have some pattern, right? But then in the majority of these kernels, regardless, like if you don't consider the one that did not learn anything, so this kernel here didn't learn much, but all the other kernels that have learned some kind of specific edge filter or shape specific shape filter, all the outside pixels have now been set to some 0 value, I think, or some value that is uniform, right? Because again, the input images now are no longer constant in the areas outside the digit, and therefore the value of the pixels, well, the value of the kernels in those specific regions now do matter. Okay, this is a big difference. And again, these maps here, these kernels here didn't learn anything. Okay, so let's now compare our denoising autoencoder with state-of-the-art algorithms for denoising images. So here we are going to be importing some functions from the OpenCV library. There is the Navier-Stokes and then the Tele algorithm. So let's import it and let's see how this stuff looks. So here, the first image is the noise image, the one we generated before. These are the maps of all ones where we have dropped out some specific values to set to 0, right? So yellow is 1 and purple is 0 in this case. Then the second part is going to be the bad images. So these are the bad images, meaning purple is -1, yellow is +1, and then this green is the 0 value. So all those black points, like purple points in the first row, are here represented in green. So those are the values that are being set to 0, they're a mask value. Then we have the original images and the reconstructions from our denoising autoencoder, which look reasonably okay if you think that half of the pixels were actually a miss, right? So these are like half of the pixels are provided to the network, and then the network actually reconstructed what looked like the original image, more or less, right? Cool. So let's now have a look to what the state-of-the-art algorithms output are. So we're going to start with the Telea and then Navier-Stokes. And so this is Telea and this is Navier-Stokes, right? So as you can tell here, the quality of our model is clearly superior in terms of qualitative output. Nevertheless, pay attention that this model works just for this kind of specific perturbation that we have introduced, and then we have learned how to counteract. Okay, so again, a autoencoder that we have trained in
in a minute performs much better than state-of-the-art computer vision algorithms, again, when data is available, okay? And so I think that's it for today. Thank you for listening. Subscribe to my channel. Turn on the notification bell if you'd like to have information about latest videos, and follow me on Twitter. Peace. Bye-bye.